Okay, so here it says that we have a point A on a circle. Okay, we're just going to say that we don't know how big this circle is. And we know this in quadrant 2, so it's going to be, we'll say that's negative A here and positive B here. Okay, and I'm going to say that this is the hypotenuse or radius is A squared plus B squared square root. Okay, so that works out to be our radius. It says point B, sorry, let's write the angle theta here. There's my theta. It says point B is the intersection of the same angle theta with a unit circle centered at 0, 0. Okay, so I'm going to draw my unit circle. And again, we don't need to, after a while when we get comfortable with this, we don't need to draw in this unit circle anymore. Okay, so that point is point B. Okay, so point B. And we're trying to figure out the x and y, the y coordinates of x and y, or in this case, we want to find out that y coordinate in terms of, it says x and y, but really it should be a and b. So we want to find this in terms of a and b. So since this is a unit circle, what we're going to say then is that this coordinate is going to be equal to cosine theta, and the y coordinate is equal to sine theta. Well, cosine theta, if I take a look at this ratio, it's going to be negative a over the hypotenuse. And the sine ratio is going to be b over the hypotenuse, or the radius. Okay, and that is the coordinates for the x and y positioning in terms of the sine and cosine ratios, in terms of the sine and cosine ratios with the variables a and b. Okay, so this is, again, the fact that we can relate the point on the unit circle directly to the cos and sine ratios. So the positioning is going to be given by the ratios. And again, this is going to be very convenient for us to be able to use this when we start dealing with other expressions. So the tan ratio can also be found in the unit circle, and the tan ratio looks like this. So tan ratio is going to be the rise over run. So sometimes we say it's sine over cos. Okay, so tan ratio can be thought of as y over x, or slope, or sine over cos. The sine ratio divided by cos ratio will give us the tan ratio. In the unit circle, we're going to say that this length here, since it's a unit circle, that length is 1. Okay, that's our radius equals to 1. Well, to get the tan ratio then, it's going to be rise over run. If the run is 1, the rise becomes the tan ratio. So this line, I'm just going to highlight it, this line out here, that where if I extend the radius, it touches up here, that highlighted line is the tan ratio. So that tan ratio now shows up as a length. And I can use this length in distance or length calculations now, because now it's a length, not just a ratio. Here it's just a ratio, but now this is showing up as a length. Okay? This is a sine length, this is a cos length, this is my tan length. Okay? There's my tan ratio, but this is my tan length. So that length, when I say tan theta, I can use this length as tan theta. So now, since it's a length, we can start coming up with other relationships. For example, the Pythagorean relationship here. We can say that 1 squared plus tan squared equals this line squared. And this line squared happens to be the secant line. Okay, so we can start coming up with, and again, this secant ratio can show up as a line, a length in the coordinate plane. Okay, so there's our length. And the reason why that's the secant is because if we do the reciprocal, okay, this cosine over the hypotenuse, that ratio is same as, sorry, the hypotenuse over cosine. Notice that it's the same ratio as the secant line over the adjacent side. Okay, so we'll talk about that a little bit more later, but this is tan ratio. This vertical line here, that highlighted vertical line, is the tan ratio as a length.